I'm curious how many of you are just going to copy down the results without writing out our definition. A critical value is one that makes a derivative equal to 0 or undefined. So, excuse me. Thinking about e to the x. E to the x has no critical values. No maximums, no minimums, no turning points, which is really why we care about critical values. But either way, we're going to find the derivative of e to the x. E to the x, we're going to let y prime equals 0. And we might as well say y prime is always defined. And 0 does not equal e to the x. So e to the, maybe we'll just say no critical values. Alright. Now sine of x has a ton of critical values, so I just went from 0 to 2 pi. So we're expecting to have a critical value at pi halves and at 3 pi halves if we know that graph of sine. So dy dx equals cosine of x. We're going to let dy dx equals 0. And we can say dy dx is always defined. We know that because we know the graph of cosine. Or we could another way to say that is dy dx is continuous. Okay, so let's see. 0 equals cosine of x. X is equal to inverse cosine of 0. And that is pi halves. And then we do, I forgot what you guys called it in trigonometry. So, oh, my pen has stopped. Man, that happens a lot. So x equals pi halves, x equals 2 pi minus pi halves. Hopefully you remember your rotations from trigonometry, and that ends up being x equals 3 pi halves. Okay, so what about cosine on 0 to 2 pi? What do we expect? Oh, we get 1 at 0, 1 at 2 pi, 1 at pi, but our job is to prove. So y prime is negative sine of x. Let y prime equal 0. Y prime is always defined. Zero equals negative sine of x. And instead of doing the inverse sign, we can actually just say x is equal to 0, x is equal to pi, x is equal to 2 pi. If you know things, you're allowed to do quite a bit less work. It's assumed you understand what's going on. You know, if you introduce inverse cosine or inverse sine, it's a lot more work. Okay, so what about 1 over x? One over x has no critical values. Well, you'll see 1 over x kind of has a critical value, but not really. Okay, so y prime is negative 1 over x squared. And we can just say y prime is never equal to 0, since that would be setting the numerator equal to 0. And y prime is undefined for x equals 0. What are we doing? We're setting the numerator and denominator equal to 0 in our heads to figure out where the function, or in this case y prime is equal to 0, where y prime is undefined. Now, 1 over x is undefined at x equals 0, so no critical values. I guess something implicit in a critical value is the graph has to exist at that critical value. Continuity again. And so kind of the same thing happens here for 1 over x squared. The only place where we're going to get a derivative undefined, let's see, so negative 2 over x cubed for the derivative. The only place we get a derivative that's undefined is at 0. And so maybe we'll do it that way. Y prime is never equal to 0. Y prime is undefined for x equals 0. But y equals 1 over x squared. Maybe we'll say something slightly different. Does not have x equals 0 in its domain. No critical values. Okay, a parabola. And this parabola has a 0 at -5, another at 0. So we should be expecting a critical value at -2.5. So hopefully these derivatives are easy. X squared plus 5x is a polynomial. All polynomials are continuous and differentiable everywhere. And if a polynomial or anything is differentiable, that means its derivative is always defined. So I'll write that. Y prime is always defined. 0 equals 2x plus 5, subtract 5, divide by 2. X equals -5 halves. Oh, now we're getting to the nitty-gritty here. So maybe I'll write down x can't be -1 in case that comes up. Alright, the derivative of a quotient of two functions is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. And we're going to have to do it now or later, so we might as well clean up that numerator. And so that's x squared minus 2x plus 2x over x plus 1 squared. So we're going to let y prime equal 0. 0 equals x squared plus 2x. And y prime is undefined for x equals -1, which is not part of the domain. So we're not counting that as a critical value. Okay, anyways, back to algebra. X times x plus 2, x equals 0, x plus 2 equals 0, x equals -2. Let's see, the cube root of x should have a critical value at 0, a vertical tangent. So this is another one you may want to memorize, 1 over 3 times the cube root of x squared. And dy dx is never equal to 0. dy dx is undefined for x equals 0. Cool. Pretty easy. The square root of 1 minus x squared, that is a semicircle centered at the origin with a radius of 1. So we'll do this the hard way, meaning not rearranging. So we expect 1, 2, 3 critical values. Those are vertical tangents where x equals 1 and x equals negative 1. Okay, so here we go. The derivative of the square root, 1 over 2 times that square root, of 1 minus x squared, which has a rate of change of negative 2x. So let's clean that up a bit. And we're looking for critical values, so we can say y prime equals 0 when x equals 0. Y prime is undefined when square root of 1 minus x squared equals 0. 1 minus x squared equals 0. 1 equals x squared. X equals positive or negative 1. Well, everything was all jumbled together, so maybe we'll write out in this case our critical values at the end. Should we do that on all of them? I think so. Critical value. Why do I keep wanting to write an S? Critical values. Maybe. Only critical value. So we don't really need to write this in the future because we're just going to use those critical values to do whatever's next. Okay, a couple more. Nope, one more. Oh, good gracious, that's ugly. Let's rewrite. Instead of the cube root of x minus 2 squared, let's do x minus 2 to the 2/3 power over x, and we'll have to use the quotient rule. X minus 2 to the negative 1/3 chain rule times 1. X minus 2 to the 2/3 times the derivative of the denominator 1 over x squared. And again, x can't be 0 from the beginning, so we're going to get what appears to be a critical value there, but not really. Okay, so x times 2 over 3 times the cube root of x minus 2. Let's put that 2 up top. See, minus the cube root of x minus 2 squared over x squared, and that's pretty ugly. So we'll multiply by the cube root of x minus 2 over itself. Because then, let's see, how am I going to write this? So x squared is going to be down here, and I'm going to move the 3 down to the denominator. And then this first part just ends up being, let's see, 2x in the numerator minus, well, this is going to be the cube root of x minus 2 cubed. And then we have an additional cube root of x minus 2 in the denominator. Okay, that looks pretty good. So 2x minus the quantity of x minus 2 and x plus 2. Really? That's a little surprising. Let's see. From the beginning, x can't be 0. Okay, here we go. So let y prime equals 0. That's x equals negative 2. Y prime is undefined. Let y prime be undefined. 3x squared times the cube root of x minus 2 equals 0. X equals 0, x equals 2. But we reject x equals 0. So critical values, x equals negative 2, x equals 2.